you very much. Also like to start off by thanking the organizers for putting this meeting together in this lovely place here, and thank you for the invitation. I was actually asked to talk about lattice effects in frustrated molecular materials, and I decided to constrain it to the subgroup of molecular spin liquid candidate systems. Maybe you have been familiar with these spin liquid candidate systems over the year, and you recognize that these organic systems were quite influential for this field of quantum spin liquids. But the discussion to that has taken some twist recently, and I thought, because of most of the protagonists are in the audience for this discussion, I thought it might be helpful to add our perspective of lattice effects to the discussion. So here's a list of collaborators. In particular, I'd like to acknowledge the contribution by the graduate student Steffi Hartmann, former graduate student Elena Agati, also in the audience will be the next speaker, now in the Max Planck Institute in Dresden, and Rudra Sekar-Manna. He's now at the Department of Physics at IIT Tirupur. Then we have an ongoing collaboration with neutron scatterers. This is Masato Matsuura, Takahiko Sasaki, and Oliver Stockert from Dresden. And then we have a lot of collaborations. We are closely in contact with the theory group. Jose and his team, Steve, is also here in the audience, now at North Carolina at the Wake Forest University. And then we have samples from several sources. I mentioned John Schlüter, Dr. Yoshida, and also Gunji Saito, as well as Harald Schubert from our team. So when we want to understand the characteristics of these molecular materials, we have to consider their molecular building blocks. And of particular relevance are these frontier molecular orbitals, which have a pi electron character. So we are dealing here with pi electrons. When they form a crystal, these pi electron loops weakly overlap, giving rise to relatively small bandwidth of the order of half an electron volt, which, however, is of the same size as these relative small on-site Coulomb repulsion, also half an electron volt. In addition, these systems have some characteristics which constrain, so to say, the ability of the electrons to screen the long-range part of the Coulomb interaction. This is their tendency to form low-dimensional structures, and the small charge carrier concentration, which is typically 1 to 2 orders of magnitude smaller than in ordinary metals. Both of these characteristics are in favor of this inter-site Coulomb repulsion. So as a result, we are dealing here with a pi electron system with the combined action of a strong U and strong inter-site interaction. In addition, what you recognize here from this looking at the figure, the chemical bondings. This involves van der Waals bonding, hydrogen bonding, and to some extent also some ionic bonding. So the lattice is weak. And in fact, the lattice is soft, and the compressibilities of these systems are typically an order of magnitude larger than you find in ordinary metals. So I'm focusing now on this kappa phase, this two-dimensional system, BED DTF2X, abbreviated as ET2X. These form two-dimensional system where the organic molecules form a layer, which is then separated by thin sheets of anions from the separate layer. And they have triggered some excitement as it was realized that some of them, particularly this system with this anion X kappa NCN2, which I will abbreviate as kappa chlorine, is located right next to the mod metal insulator transition. And you need only a small pressure of only 300 bars to drive the system into the metallic and then superconducting state. So with such a system at hand, you can access the mod transition and do some investigation of the mod and the mod critical endpoint. And I think Elena will discuss this in more detail. Further excitement came in by this work by Shimizu and collaborator in 2003, when they discussed this material, this kappa 2, 3, and 3, which I will abbreviate as kappa CN. And they found that in this system, instead of undergoing a long-range anti-ferromagnetic order at low temperature, it stays non-magnetic down to the lowest temperature. And this was, so to say, the birth of these quantum spin liquids in these organic family. So what is clear, we are dealing here with weak mod insulators. They are located close to the metal insulator transition. Depending on the anion you choose, you have varying degree of frustration in the system, and this kappa Cn is a promising quantum spin liquid candidate system. So this is the outline of the talk. I will mainly focus on this kappa 2 Cn3, and we'll do some recap on experimental observations, including the lattice effects. And then we'll show some recent data on phonon renormalization effects, which we found by studying inelastic neutron or doing inelastic neutron scattering. And then at the end, I will come to this isostructural system where the kappa is replaced by silver and ask, are there any differences? And in fact, it turns out there are differences. And due to some tiny structural details, but this seemed to matter in this system. Okay, when discussing the properties and want to classify these different materials, one has to look at the electronic structure. So in this kappa phase, the organic molecules tend to form dimers with a close face-to-face interaction, and neighboring dimers are alternating their orientation throughout the structure. In these two compounds here, the interdimer transfer integral, labeled TD, exceeds the interdimer transfer integral by a factor 4 to 5. And this led many people to think of these systems in an effective dimer model, so representing each dimer by an effective site. And because we have in this 2-to-1 stoichiometry, we have one charge carrier is transferred to the anion, we have one hole left on the per pair of ET molecules. So we have one hole per dimer. We are in a half-filled situation. And now these dimers form a triangular lattice with these hopping terms T prime and T. And the degree of frustration is given by the ratio T prime over T. And when we go from the anti-ferromagnetic ordered system, where this is moderately strongly frustrated, 0.44, to the spin liquid candidate system, this goes close to 1, 0.86. Now, at this point, I already like to mention another system which fits into the scheme, which is also a kappa phase material with this anion mercury, SC, and chlorine. It has a degree of frustration which is similar to this one here, strongly frustrated, but a degree of dimerization which is slightly less. I'll come to this later in the talk. Okay, now the story began when Shimizu reported the DC susceptibility measured by squid. This goes over a maximum and then drops down, but stays finite at low temperature. The data could be reasonably well fitted with a spin 1/2 triangular lattice Heisenberg antiferromagnet with a J of 250 Kelvin. Looking at the proton NMR, the protons are sitting a little off the pi electron system. What they found is that the spectrum does not change on cooling from 36 Kelvin down to the millikelvin regime, which is quite different from what you find here for this chlorine material. I apologize, probably very small, these labels, but this is the system which orders anti-ferromagnetically, where you see the splittings of the line. So whereas to have line splitting here, this is absent here. So there's no indication for long-range magnetic order down to 30 millikelvin are consistent with this notion of a quantum spin liquid system here. And then people focused on the low energy excitations in the system to understand what kind of quantum spin liquid is realized. And I show you here data of the specific heat after subtracting a nuclear contribution, plotted as C over T versus T squared. And the data form a straight line and have a finite intercept here, indicating that we have fermionic-like excitations in the system. But this was challenged by measurements of the thermal conductivity by M Yamashita. This was S Yamashita, here by M Yamashita. And when you plot the data in a similar manner, kappa over T versus T squared, there's no finite intercept here, indicating that there are no indication for gaplessness, whereas they find indication of a small spin gap of about ½ a Kelvin, which is a tiny fraction of the exchange coupling constant J. Then what also was observed is here in the specific heat, a mysterious 6 Kelvin anomaly, which was only a side note in this publication. which shows up in the shoulder here in this C over T versus T square. And when you subtract some background contribution, you get a hump-like structure in the specific heat. This was associated or attributed to crossover to a quantum spin liquid state. When you look, however, on the thermal conductivity, this was reported in this M. Yamashita paper. There's quite a significant change here in the thermal conductivity, a step-like increase, and some significant sample-to-sample variation. And for me, that looked like a phase transition. This we know from superconductors. It looks like that. The thermal conductivity recovers once the spin electron scattering freezes. So in order to check for a possible phase transition, we did some measurement of the thermal expansion. And this is data back in 2010, when we studied the in-plane expansion coefficient for this material, and we found huge anomaly. So the ordinary lattice contribution, you could hardly discriminate here from the zero line. And you here see anomalies which goes up to 8 times 10 to the minus 6 per Kelvin. So there are really strong lattice effects with a pronounced in-plane distortion. So this is C-axis data. This goes along this axis here. B-axis data. This is this. We found no hysteresis upon cooling and warming. And what can also may recognize, there's no effect of a magnetic field up to 8 Tesla. So the 8 Tesla data are the green symbols that directly lie on top of the zero field data. So this led us to conclude at that time, we apparently have here a second order phase transition with a strong coupling to the lattice degrees of freedom. In the same paper, we also published this data of the specific heat, taking here the tiny single crystal of 100 micrograms. These are the red symbols here. And when you subtract some background contribution, you recognize there is a hump, the specific heat. And then we plotted this data, and this is here these open circles. This is the specific heat, and they directly fit to the thermal expansion data. Here, this is the C-axis data. This is the B-axis data multiplied by minus 2.5. And what we also plotted is the susceptibility as d chi dt. These are this data here. So first of all, from the fact that specific heat normally scales with thermal expansion, normally scales with d chi dt, this is something which you expect for a phase transition, but not for a crossover. In addition, the fact that you see an anomaly in d chi dt indicates to you that spin degrees of freedom to some extent are involved in this transition. And now when we build the difference here between the background and the measured data, we could get an estimate of the entropy involved in this transition. And we found a number of about 7 to 8% of RLN2 for 1 mole of spin 1/2 entities. Now this quantity you can compare with the remaining spin entropy you would expect for an hypothetically ideal 2D triangular lattice spin 1/2 system at temperatures of 4% of J, in our case 10 Kelvin. Unfortunately, this is available only for the fully frustrated system T prime equal T. If you assume purely Heisenberg interaction, what you would get is that below 10 Kelvin, there's remaining entropy of 2.3% RLN2. If you allow ring exchange processes, which are likely to be present here because we are so close to the Mott transition, we are weak Mott insulators, and which are likely to account for the fact that the system does not order anti-ferromagnetically. So then this goes up to about 5.2% of RLN2. But there's a difference here. And so at that time, we claimed that spin degrees of freedom alone cannot account for this anomaly in the specific heat. And it turned out that around the same time, a paper appeared by Majid Abdel-Jabbar, where they studied the dielectric features of the system. And what they found is a peak in the dielectric constant, broad peak. When you increase the frequency, decrease the frequency, you recognize the peak increases and grows in size. But this is typical response of a relaxer type ferroelectric, where you have clusters of disordered clusters of ferroelectric ore. What they also observed is that the peak position follows a Curie-Weiss-like temperature dependence, with a Weiss temperature, so an ordering temperature, lying close to the 6 Kelvin, indicating that there could be some correlation to the 6 Kelvin anomaly. The different curves are simply for different frequencies. So this is the highest frequency, and this is the lowest, in this case, 500 Hertz. So the scenario which they put forward in this work, and which was also discussed in a number of theoretical papers here, is they assigned it to intradimer charge degrees of freedom. So the idea was that within the dimer, the charge is fluctuating, which would correspond to fluctuating dipoles, electric dipoles. And once the charge gets ordered due to charge ordering, then a ferroelectric state occurs. This was, however, challenged by Martin Dressel's group doing infrared spectroscopy, which failed to detect any charge disproportionation within the experimental resolution, which is about 0.5% of an electron charge. So the point which I want to make here is that the observation of a dielectric anomaly in this system is not an exception, but it turns out that it is rather the rule. So when you take for comparison the chlorine material, which orders anti-ferromagnetically, we found back then in 2012, together with Peter Lunkernheimer and with Jens, that there is a pronounced peak in the dielectric constant. In this case, the peak size grows with decreasing the frequency, but the peak position stays constant. And this is a typical sign for an order-disorder type ferroelectric transition. And when we go to this material which I introduced in the beginning, this mercury chloride material, which has a degree of dimerization which is a little less. And what we found here together with Elena was there is a huge peak in the dielectric constant, abrupt drop. And this was a sign for a first-order ferroelectric transition. I also like to mention here at this point that in the poster tomorrow, Yasin will show another kappa phase material, this kappa Betz mangan system, where the degree of dimerization is 3.5, where we also find dielectric anomalies. So these dielectric anomalies are, so to say, inherent to this material apparently, and highlight the importance of these interdimer charge degrees of freedom. Now, then the discussion became a new twist by this paper by Miksch et al. In Martin's group and with Andre co-authored, where they studied the ESR, and here showing the susceptibility derived from the ESR experiments. And they argued that in the ESR, they are able to discriminate between different contributions, and namely the intrinsic spin susceptibility plus an impurity contribution. And when they plot the spin susceptibility, what they find is an opening of a gap around 6 Kelvin and a vanish of the spin susceptibility. In addition, they were able to identify an impurity contribution that then dominates at low temperature. And what this implies for all the data which I've shown you before, this is, you can imagine, and I'm curious to see the discussion later to discuss some issues on that. Okay. So the effect of disorder was also pointed out by this work here by Kira Riedel, Steve Winter, and Rosé. What they did was they analyzed magnetic torque data published by Isono and collaborator. And what they argued is, given that the system is very close to forming a valence bond solid, indicated here. So each of these dots here represent a dimer, and these dimers then tetramerize. If the system is close to that, then what is happening, that disorder induces some defect spins. And they discussed two different types of disorder. One type, this type B, comes from random modulation of magnetic interactions, which gives rise to this domain structure here, leaving behind an orphan spin. One type of disorder. And the other comes from defects in the anion layer, for instance, kappa 2+, which is a kind of a local doping, leads to a charge imbalance in the ET layer, a spin vacancy, and this gives rise to a broken bond, and there's an unpaired spins remaining here. And what they suggested is that a bunch of experimental data could be explained in a scenario of a valence bond glass ground state for this system. Now, the presence of these defects led us to reinvestigate various samples by means of thermal expansion measurements. And overall, we studied 9 different crystals from various sources to look for sample-to-sample variations in these lattice effects. And I show you here, so to say, the effects of the 2 most extreme cases. The one is these solid lines. This is the data we published in 2010, and the full symbols correspond to more recent data. What you recognize here is thermal expansion goes highly anomalous. There's this broad maximum here, and then the B-axis data goes down, seems to cross even the 0 line. This is very strange. Also, the C-axis data varies linearly in temperature, which is strange, and then goes to this minimum here. But what you also can see that in this temperature window here, there's no significant sample-to-sample variation. So within the error bars, they fall on top of each other, so only small sample variations. However, when we now look at what happens at low temperature, and this is the blow up we're seeing here, this is the data I've already shown you, where the peaks were pretty large. But now on this, so to say, the best crystals, these are extremely large. And now there's no question that this is a phase transition, in my understanding. So it becomes pretty sharp, this anomaly. We can clearly identify it as a second order phase transition. It keeps its anisotropy. So if you multiply this by minus 2.5 or 3, you get the C-axis data, and this is the same as for the first crystal. There's no field dependence. So no field dependence within our experimental resolution. And we have a significant sample-to-sample variation in the size, but not in the transition temperature. There's only a very mild change in the transition temperature, while the size is pretty much sample dependent. Now, looking at this transition, this is very much reminiscent of what we found earlier, looking at this TM-TSF ASF6, which undergoes a spin-Piles transition. So this suggests that what we are dealing here with is sort of the 2D version of this spin-Pile. This would be a valence bond solid transition. But this is a dangerous becomes clear when I show you here the transitions which we found on really established valence bond solid systems. This is a palladium DMID system which undergoes a transition into a valence bond solid at 25 Kelvin, where you see here in the expansivity, this looks like a mean field-like transition. Or when you compare it with this kappa ET2, this boron containing system, which also undergoes a valence bond transition at almost the same temperature as our kappa 2C and 3, namely 5 Kelvin here. This looks like a broad king, but some significant field dependence we have here. So the point which I want to make is there's no clear conclusion we can draw from this similarity to the spin-Piles transition so far. Okay, to get a little deeper insight in what is going on, we initiated some inelastic neutron scattering on this salt. And here are the main players. This is Takahiko Sasaki, also provided the single crystals. Overall, we measured a collection of 47 single crystals, well aligned, with a total mass of 26 milligram. And here are the guys who did the experiment. This is Masato Matsuura and Oliver Stockert. Experiments were done at the triple axis spectrometer at this instrument IN8 in Grenoble. And in order to have a good choice on the momentum transfer you want to look at, we were guided by our experiments back in 2019 on the chlorine material. So in the chlorine materials, we looked at this intradimer mode here, indicated here, and found that this mode is very sensitive to what is going on in the electronic channel. We found strong renormalization effects, which couple to the spin and charge degrees of freedom. Now, in order to make the scattering intensity large, you have to make this product Q times Xi, the square of it, to make it large means you need a large momentum transfer, which in the ideal case should be parallel to the polarization mode vector of the mode you are looking at. And this is fulfilled for the 603 momentum transfer, which is large and which is practically parallel to Xi. And since in our kappa 2, C, and 3 material, the symmetry is a little lower. It's a monoclinic symmetry, which implies two structural domains which share, however, a common b-axis. So we selected this 060 Q vector, which has a large component parallel to this displacement vector, this mode vector. So this was the Q vector we selected for this experiment. And here are shown now a selection of constant Q scans taken at temperatures 10 Kelvin, 8, 6, 5, and 1.5 Kelvin in an energy window below 8 millieV. So what you recognize are these peaks, some of which are more pronounced, others are less. And these peaks actually can be identified to phonon peaks based on these DFT calculation, which were published in the supplement of this paper by Martin back in 2016. And particularly strongly involved is this mode here at 4.7 millieV, which shows strong changes. And this mode, according to this calculation, is this intra-dimer breathing mode. And you recognize that this mode undergoes strong changes when you change the temperature in this window. Now, by using damped harmonic oscillator functions to fit the spectrum, what you recognize is there's a strong renormalization going on with this mode. This mode is very broad at 10 Kelvin, much broader than the experimental resolution, which is this bright bar here. It stays broad at 8 Kelvin, but then suddenly becomes very narrow. So there's a drastic change, and this can become particularly clear when you look at the temperature dependence of the fitting parameters. And here I just want to focus on this subgraph B, where the line width is plotted as a function of temperature. You see a drastic change in this damping, which is inversely proportional to the line width. It stays constant and large up to 100 Kelvin, and then suddenly within 2 Kelvin gets reduced into a resolution limited long lifetime of this mode below 6 Kelvin. So apparently what is happening here, that there is a phonon which scatters with something, and this scattering process becomes ineffective or frozen once you cool below 6 Kelvin. And of course, the question is, what is the nature of these scatterers? And I found it very instructive to look at the phonon modes at 100 Kelvin. We look here at what happens at 100 Kelvin for our spin liquid candidate system. You recognize that these modes are very broad. You can hardly find any peak structure. If you compare it with the copper chloride material, you recognize there at 100 Kelvin, you have well-defined phonon modes in this energy window. Now, when we go back to our analysis back in 2019, what we found is that the damping of this mode corresponding to this data is small at 100 Kelvin, but starts to increase once you cool the system into its insulating regime. So once the charge gap is opening, once the electron is no longer delocalized and starts to hop onto the dimer and becomes localized on the dimer side. Then the damping increases, and the damping then starts to decrease once you have ordering phenomena in the spin and the charge channel on the dimer side. Then the damping becomes reduced again. So this suggests that this damping is related to the charge localization on the dimer. This provides really a rationale to understand this data. When you look at the resistivity here, when we do the scattering at 100 Kelvin for the copper chloride material, we are above, so to say, the Mott gaps opening. Pi electrons are still itinerant, and here they start to localize. Whereas in the kappa Cn, they are already in the Mott localized state. So this suggests for our spin liquid candidate system that the phonon damping is somehow related to the charge and maybe also spin fluctuations on the dimer side, and that the scattering of these fluctuations is then frozen below 6 Kelvin. Now for the remaining 10 minutes or so, something roughly, okay. So I want to discuss result on an isostructural system where the copper is now replaced by silver. And it was found by Shimizu. This system is younger than the other one. It was found by Shimizu in 2016. That the phase diagram looks very similar to the copper variant, except there's an offset on the pressure axis by about 0.6 GPa. So apparently we are somewhat deeper in the mod insulating state here. A fit to the susceptibility, also, which is also works reasonably well, gives you a Heisenberg interaction of about 175 Kelvin. And as for the copper system, there's no long-range order found down to the lowest temperature of the experiment, which here is about 100 millikelvin. The low temperature specific heat also shows this linear variation with temperature in this plot C over T with T square, and giving this finite intercept here at a gamma value of about 10 millijoule per mole in Kelvin square, not so different from the copper variant. But there is an interesting and intriguing difference in this system in the anion lattice. And this highlights the role these anions have in templating what is going on in the ET channel. So both systems share these zigzag type chains where these transition metal ions are connected via CN groups along these chains, and these CN groups are ordered. Two adjacent zigzag chains are coupled via CN groups, and since these CN groups are sitting on inversion symmetry centers, there's some intrinsic disorder associated with it. And this is also the same for both variants. Now the difference comes how the ET molecules are oriented with respect to these anion layers. In the case of the silver system, the ET molecules, which are represented by this green ellipse, are centered directly below this disordered CN group. Whereas for the copper system, the ET molecules are centered in the center of these anion openings here. And this might have an effect on the bonding between the ET molecules and the anions. And this was pointed out, I think, first in this paper here. There is a short distance between the ET molecules and this CN group, or the protons between the CN groups and the protons of the ET molecules in the terminal ethylene groups. And it was speculated that this might, so to say, have an impact on the conformational degrees of freedom of these ethylene end groups. And in fact, what was found is that for the silver system, these ethylene end groups are ordered already at room temperature. Whereas for the copper system, they are disordered. Disordered means they can fluctuate. In both cases, these ethylene groups are ordered once you cool the system. So here at 150 Kelvin, they are ordered. This sounds or may sound like a minor structural detail, so whether ethylene end groups are ordered or not, so who cares? But now, going back to the thermal expansion, which I showed you in the beginning here for this copper 2 CN3 system, where I pointed out that the expansion coefficient behaves very anomalous in this temperature window here. So the B-axis is strongly reduced. The C-axis shows a linear variation up to high temperature. There's this upturn here in the A-axis, very anomalous. If you compare this now to the silver system, everything looks much more ordinary. So the phonons here, the lattice contribution is much more Debye-like. It just grows with increasing temperature in a smooth manner. This suggests that all this anomalous stuff here in the expansivity comes from this ethylene end group motion. A tiny structural detail which may have a strong impact on what is going on in this system. On the positive side, now this seems to be absent here for the silver system. And this allows us now to extract these anomalies here, which are located around 12 Kelvin or something, this minimum here, and which becomes apparent here, since the lattice contribution is so harmless. And this was done in this work here. So we extracted an anomalous, we called it electronic contribution. And we simply assumed that there's some kind of generic form of the electronic contribution, which is the same along all these axes, but just is different by sign and a prefactor. And we also assume that the lattice contribution follows some generic form. And then we can do some different combinations of uniaxial expansion data. And out of this, we constructed, this is so to say, this anomalous electronic contribution. It's a peak around 20 Kelvin with a very steep slope here in low temperature and a gradual decrease here at high temperatures. And this is so to say the thermodynamic response of this strongly frustrated quantum spin system for this given degree of frustration and Heisenberg exchange J. And interestingly, this has been predicted already by this paper back here in 2015 by Kokagi and Ross Mackenzie. They studied the Hubbard model on an anisotropic triangular lattice and used model parameters for the spin liquid candidate system for the kappa 2CN3. So we are in the mod indulating side. And what they found in their calculation is very similar to what we found actually experimentally. A peak type anomaly, which is steep decrease here on the low temperature side and this gradual decrease in the high temperature side. A strong anisotropy. What they argued in this paper is that the position of this peak and actually the anisotropy is very dependent on the choice of these Hubbard parameters, of course. And this is shown, for instance, by if you calculate this anomaly for a frustration ratio T prime over T of 0.8, you get the blue and the red curve. If you do it for 1.2, then you get this broken line. So the anisotropy is reversed and the anomaly is smeared out strongly. So they can and this is also apparent, that the thermal expansion is a quite sensitive tool to extract these Hubbard parameter rather precisely in this system. So an immediate consequence or an immediate conclusion we can draw is now back to the silver system. Now here plotted is the low temperature part on expanded scale. Now, given that the thermal expansion coefficient is nothing but the derivative of the entropy with respect to uniaxial pressure along the same direction with this minus sign. So from this positive anomaly, which we get here, means that increasing uniaxial pressure along the c-axis, so this is the c-axis, increasing uniaxial pressure along the c-axis means we essentially increase the hopping term T. This is accompanied by a decrease of entropy. On the other hand, from this negative contribution here along the b-axis, we can claim that increasing uniaxial pressure along the b-axis, which essentially increases T prime, this increases the entropy. Now, if we assume that there will be a maximum in the entropy at the isotropic point when this ratio is 1, then these two conditions can be fulfilled when we are sitting here on the left side of this maximum, when T star over T is less than 1. And this is actually what is found also by extended Fickle calculation, by Bunji Saito, and also by Steve Winter's exact diagonalization work. The B axis, this. Excuse me. So the B axis is this axis here. So note that these are dimers. These are dimers, and these are so each point represents a dimer, and so I cannot give you the numbers actually. Yeah, because the orientation is the orientation matters a lot. So 1.7. So then we have to, maybe we go. So maybe we check it later. So I have to go to the. Okay, we check it later. So given that this maximum in the entropy is here, so the system is here, and this is consistent with what actually has been predicted. However, for the Kappa system, we do the same type of arguments for the Kappa system. We would get because there the anisotropy is reversed, we would get a ratio T prime over T which is in excess of 1. This is not consistent with the work by Harald. However, in Steve's paper, this is what you found in your work, Steve. So apparently there is some question related to this. So this brings me to the summary of what I've shown you is in this kappa 2, 3, and 3, I think we have clear indications for a second order phase transition occurring at 6 Kelvin, which is accompanied by pronounced in-plane lattice distortion. There's actually no field dependence within our experimental resolution up to 8 Tesla. We do see a significant sample-to-sample variation in the size, but not in the position of this anomaly. With the inelastic neutron scattering, what we found are pronounced phonon renormalization effect in this intra-dimer breathing mode at 4.7 millieV, which happens to occur right around the 6 Kelvin, which has a strong damping for temperatures above 8 Kelvin up to 100 Kelvin. This was the highest temperature of the experiment, which seems to indicate some correlations to the charge and maybe the spin fluctuations on the dimers. And this scattering becomes ineffective once we cool below the 6 Kelvin anomaly. In addition, what we observed is anomalous and very large lattice effects at high temperatures, which by analogy to the silver system, we assigned to this ethylene end group motion, to the disorder of the ethylene end group. This may have really a strong effect. They seem to artificially strain this system. This is absent for the silver system. For the silver system, we have ordered ethylene end groups. The lattice behaves like an ordinary material. This enables us to access this electronic contribution, these anomalies around 20 Kelvin, as, so to say, the thermodynamic response of this triangular lattice spin 1/2 system, and which is consistent with theoretical predictions. Within our temperature window, we find no indication for a phase transition anomaly. And to finish up with a positive note, this material is still a good candidate for a quantum spin liquid ground state, I guess. So with this, I'd like to thank you for your attention.